All right, what did we see last time? We saw the Laplace transform as an infinite integral. And then this is where we change from a t function to an s function. And then in the Laplace world, we're using capital letters to denote our functions with the independent variable s. And then in the real world, we're using lowercase functions um, with the independent variable t. We use a script L to symbolize that we're doing a Laplace transform. We're sending our function to the Laplace world. Laplace is a linear transformation, which means it's closed under addition and scalar multiplication. We scalar multiply and then we add, and then we're going to get. It's not closed under multiplication, and so for that we need to introduce something different. We have some basic Laplace transforms. We show the Laplace transforms for 1, t and t squared, and I think we said, without really proving it, we can generalize to a power function as just n factorial over s to the n plus 1. There's also the exponential function gets taken as a 1 over s minus a, whatever the coefficient of the power is. We have a couple of trig functions, sine and cosine, and then the hyperbolic functions are really just some linear combinations of exponential functions. So here are some basic transformations. And I won't bother trying to prove that, but you should prove one of these functions. So it'd probably be a good test question to have you prove one of these Laplace transforms, just for the sake of proving it. So you should be ready to prove one of those during your final exam. I probably won't do the sinh or cosh, but anything up here between the L to the some power, e to the at, or sine or cosine, you should know how to prove it. If it's a sine or cosine, if you look back at the definition of the transform, there's an e to the st, e to the negative st involved. So in your sheet of notes, you probably should have some of those integrals, like the integral of e to the at times sine dt or something. You guys remember that in Calc 2? You have an exponential and you have a trig function. You have to do integration by parts and then subtract it over to the other side. And things cancel out. So I don't want you to do all that work. If you have the formula for the integral, then you don't have to do the weird integration by parts. I don't know if it's proved in the book. It might be an exercise saying, hey, you guys should be able to prove this. Kind of like what I'm doing. Hey, you guys should be able to prove this. Yeah. Prove. So prove, for example, prove that this is the transformation for sine kt, for example. And then, yeah, so basically run it through the transformation. All right. So we're going to also, I'll mention a few other things that we're not really going to talk about. It's of little consequence, and we're kind of behind already. So there's some theory behind the whole idea of being able to do Laplace transforms, or what types of functions that we can do Laplace transforms on. And it says here that they give a definition for the thing called an exponential order, and that your function is of exponential order if it satisfies this criteria. You guys have known piecewise functions since Calc 1, I think, right? So we're going to be dealing with piecewise functions. Piecewise continuous just means it's continuous, except maybe for a finite number of places where it's not. So a piecewise continuous function on some interval says that it's going to be continuous everywhere except maybe for a finite number of points where it's not continuous. And usually these things mean that they're integrable. That means you can integrate over them. And there are definitions where you can integrate a function like this. So we don't want to mess with other functions that are discontinuous at an infinite number of points. That's weird. There are functions that are discontinuous at an infinite number of points. Yeah, if you look back at Calc 1, they'll have these weird examples that hardly ever come up in real life anyways. So a function is of exponential order if there exists some constant and some capital T, so that f of t is smaller than some other exponential function. So those basic functions that we were looking at are examples of functions of exponential order. This just says that there's going to be some exponential function that's going to bound your function. So your function is going to be less than that. And we know that if you have any big T for all t values at some x value or t value, it's going to be true. And then the next two talk about, the next theorem talks about conditions for existence, that a function has a Laplace transform if it's of exponential order. Yes? Well, the resulting Fourier or the resulting transforms, Laplace transforms, in this next theorem says that they all kind of go off to 0 as x goes off to, or s goes off to infinity, and so it's not. I don't see that same correlation with the Fourier, because the Fourier transforms were more like talking about the visualization is about the Fourier series, and the series is something that we can visualize with the square waves and other kinds of waves and stuff. Yeah. So I'm not sure. Yeah. All right. So this is like the existence and uniqueness theorem in the beginning of the semester. This is we're not going to dwell too deeply on this. I'm more concerned about just being able to perform the Laplace transforms and the inverses. So remember that picture that I showed you guys, that going to the Laplace world and doing our work using algebra in the Laplace world. At some point, we need to find our way back to the real world. And so to do that, we do the inverse Laplace. So if you just kind of remind you of the picture that we had, real world, we got our differential equation here where we would use calculus to solve and get the solution. And then we go into the Laplace world. And to go into the Laplace world, we need to do this Laplace transform. And then now you have just instead of a regular differential equation, you would have just an equation. Where you do some algebra. But then you have to come back. So that's the part that sometimes that could be the difficult part, is to take the inverse Laplace, come back to the real world, and translate your solution back into little y of t. And so the process for going back will not have to worry about doing an integral. I mean, you can do an integral to go back, but you should just be able to look at your function, and we already have a set of Laplace transforms that has its way to go back, inverses. So our key is to make it look like one of these functions that we already have, that already exist. And by looking at one of these functions that already exist, somehow translate it back to one of these functions. Yeah, so a lot of these things have fractions and stuff. So yeah, partial fractions are going to play a big part in doing this. So the inverse transform is also linear, just like the regular transformation, which means if we have two things that we're adding, or if we have a constant times something, then we can just factor those things out. So a good exercise might be, I don't know if we have some examples here. Sorry, I'm going to go to the book and see if I can find a problem to do. Isn't this your textbook? No. Oh, it's another edition. So let's do one of these, a few of these problems to get us practicing our inverse Laplace. Let's copy the whole thing over here and then see what we can do. And do you guys have the table memorized already? No? Okay. All right, so for example, let's take the inverse Laplace of 1 over s to the third power. Well, 1 over s to the third power looks like 1 over No, it was like n factorial over s to the n plus 1, right? And so what we want to do is we want to make it look like this. We have a 3. This is to the third power, so n must equal to 2, right? But we don't have a 2 up in the numerator, 2 factorial. So what we could do is we can take out a 2 factorial by multiplying it by 1/2. So the L inverse of 1 over s cubed is the same thing as the L inverse of 1/2 times 2 factorial over s to the 2 plus 1 power. And because the inverse Laplace is linear, this is like a 1/2 that can go outside, and then we do the Laplace, inverse Laplace of this. And what is that? T to the 2, t squared. So that's your inverse. Okay? That's not so bad. Gotta start somewhere. Let's try another one. Let's try number 10. Number 10 looks a lot like s minus a. Is it a or k or a? Looks a lot like 1 over s minus a. So it looks like this exponential. But it's not exactly that form. So what do we need to do? It looks like we might need to factor out a 5 from the denominator. Again, this is all algebra. So 1 over 5, and then I have an s minus. Now I have to factor a 5 out of the 2, which doesn't factor nicely. So we'll just force that. And try to write your 5s differently from your s's. So now you have a 1/5 sitting there. As a constant, and then you have 1 over s minus 2/5. So there's your function. Yeah. Manipulating it with some algebra to make it look like whatever it is you make it look like. You need to make it look like. And you need to make it look like one of these 1, 2, 3, 4, 5, 6, 7, one of these 7 functions. Actually, the sinh and the cosh, if you look at it and you factor out the s squared minus k squared, it's like s minus k a plus s plus k. So if you don't already know, the sinh and the cosh are actually linear combinations of exponential functions. And you can kind of see that here with the relationship. So we really don't need these 2 functions, because if you want to break it down, you can do partial fractions on that and make it look like the exponential. Anyways. It should always have a specific solution. Yeah, so this is your y of t. If at the end of your algebra work in the Laplace world gives you a function that looks like 1 over 5s minus 2, and you need to go back to the real world, so that's the last step that you need. So in your last step, what you need to do is you need to translate everything to make it look like one of those functions. Let's do one more. Let's do, we didn't do any partial fractions here. Let's do number 15. So that's inverse Laplace of 2s minus 6 over s squared plus 9. So the s squared plus 9 is an irreducible quadratic, and it's probably going to be a sine or cosine. And looking at this, it looks like I can break this up to 2s over s squared plus 9 minus 6 over s squared plus 9. I mean, s squared plus 3 squared, right? Because you want to identify the thing. So for the first one, we have a 2, and then we have s over s squared plus 3 squared. So the constant 2 can go outside. And then for the second one, we have a 6. S squared plus 3 squared. So if you look at the sign transformation, it's k over s squared plus k squared. So we want the correct constant to be up here, which is 3. 3 doesn't equal a 6, though. How do you get 6 out of that? Multiply it by 2. Okay. So now here we go. We have 2, and then s over s squared, that's cosine 3t. And then we have a minus 2, and then now we have the sine 3t. Okay. So that's a little practice in trying to go back from the Laplace world to the real world. Should probably do one with partial fractions, but we'll probably run into that later anyway, so just be ready for it. No, I'm not going to do it. All right. So differential equations going into the Laplace world. The last thing we need to do is to figure out how derivatives go into the Laplace world. We should do some, should always do stuff, but. So the idea here is to see what happens when you take the derivative. So the question is, I'll use curly brackets. Curly brackets. So the question is, what happens to a derivative when we try to send it to the Laplace world? So the idea is to go through the proof. So I'll go through a proof of one of them, and then I'll just put the general statement over here. But the idea is to use the definition of the transformation, which is this integral, and then the function that you're trying to transform, and then e to the minus st dt. Is that right? I hope that's right. Okay. All right. So now it looks like a job for partial fractions. No, parts. Integration by parts. So if we do an integration by parts here, I need to let u equal to something and then dv equal to something. so I can get du and u. At least this is how I used to do it. So this is the derivative, which means you take the antiderivative, you can get back the original function, right? So that's probably a good thing to put for dv. And then our du must equal to the other one. So the derivative of this is, there's a minus s come out to st. I never put enough room there for the dt. So the antiderivative of f prime is just f. And so this is going to be uv, so f of t e to the minus st minus the integral of v du So f t times minus s. Oh, you're going to take the, yeah, let's do that. So we have f of t e to the minus st taken from 0 to infinity. I'm being a little bit more relaxed with the limit as b goes off to infinity. And then this should be a plus s integral from 0 to infinity of f of t e to the minus st. All right, so the question is what happens when this thing goes off to infinity. Now we're assuming that these f functions are of exponential order, which means that we can allow our exponential function there to dominate, and that would send everything to 0 before f of t can do anything for itself. So let's say this is going to be 0, and then what happens when you put 0 in is that when you put, these are t values, t goes to 0, we have f of 0 times e to the 0, right? That's just 1. So we have a minus f of 0 here. And then we have an s times, what is this? How can we do that? Do we need to do integration by parts again? Yeah. Wait. This is the original Laplace transform of f. So the inverse Laplace transform of one derivative is going to be s times the Laplace of the original function minus f of 0. So that's just the proof for the first derivative. You can imagine if you do the second, third, and fourth derivatives, see what might happen. You'll have to do integration by parts several times until you get to an integral where you just have f of t without the derivatives, and then you can express your Laplace looking something like this. Yeah. Because of, we're just going to assume that f is of exponential order, and this is the hand waving that I did over here with some theory, that that function is going to be necessarily smaller than some function for a large enough t value. No, that's unless you really want to. And you don't know how much or how fast it's going to converge, but you know it's going to converge within this this interval. Yeah. All right. So in general, the nth derivative, the Laplace transform of the nth derivative is going to be s to the nth power times the Laplace transform of the original function minus all these other things. So depending on what order your differential equation is, you'll get to use these things. And notice that you have, these are all just going to be constants. And so these constants will play a part in the sense that your differential equation should have an initial condition, a set of initial conditions, and these constants will be your initial conditions that you're using. All right, I think once we have this information, the way to go back to inverse means we can probably solve a simple differential equation already. So let's attempt to do that. Yeah. F has to be piecewise continuous. It doesn't have to be a piecewise function. It could just be a regular function. But in some cases, we want to be able to deal with piecewise functions. And in the past, the way we dealt with piecewise functions is that we break it off into pieces and then do two separate problems. But now we'll see that with this, we have to define one special function to allow for the piecewise. Then we can do all this in one shot instead of having two integrals, or three if you have more pieces. All right, let's do a problem. Let's solve for one of these problems that we should already know the solutions to. Let's do number, I don't know. Oh, we're going to get the correct answer. I don't know. Let's do an odd problem then. Which one? Let's do a first order. Let's take things slow. All of them you can do without Laplace. In theory. I mean, by the time you get out of this class, you can do all these without Laplace, right? I mean, the first one is just a first order differential equation, right? You get integrating factor. The second one, you can bring the y over, so that's just an exponential. Well, the first, yeah, you could do that too, separable. And number 35 is some exponential functions. I mean, yeah, you should be able to do all these, right? God, I hope so. All right, let's do this as an example. If somebody wants, you guys can find the solution using, no, that's probably the last thing you want to do. We could find the solution using, finding the, what's that called? Characteristic polynomial. Is it called a characteristic polynomial? Auxiliary. Yeah, it's auxiliary equation. Auxiliary. Characteristic polynomial is eigenvalue stuff. You can. All right. Let's do this. So we have a second derivative, and what I'm going to do. So this is our real world problem. Yeah, we need to know. Yeah, if you don't have initial conditions, then it won't work. We can. All right. Let's see. We transform everything over. We're going to say that this is y double prime. So the n is equal to 2 according to this. So I have s squared. Now I want to represent y. I write my capital Y is kind of funny, but I need to distinguish it from my lowercase y because I'll be living in the Laplace world at this point. Minus s to the first power, and then I have my y of 0 term, and then I have my s to the 0th power times y prime of 0. So that's my y double prime, right? And then I have a plus 5 y prime. So I need my y prime, and that's n is equal to 1 in this formula. S to the first power times the unknown y function that we're trying to solve for minus y of 0. And then I have a 4 times the y of s, and this is all equal to 0. So now you're in the Laplace world, and all you're going to do is algebra, and you're solving for capital Y. Okay? So let's put in those values. We have y of 0 is equal to 1, and y prime of 0 is equal to 0 from the initial conditions. So we have s squared capital Y of s minus s plus 5s capital Y of s minus 1 plus 4 capital Y of s is equal to 0. So we can bring the s over to the other side, plus 1, and then everything else has an s term in it, or a y. So your y of s is equal to s plus 1 divided by s squared plus 5s plus 4. So we're done with the algebra. Easy, right? So now we need to send it back to the real world. so So now you need to send it back to the real world, which means you have to make it look like one of those things. And so this is our s plus 1 divided by, does this factor to what? Well, the s plus 1's cancel. Apparently. So we don't have to do partial fractions, and we have the solution now. So this goes back into the real world as e to the, there's no constants even, huh? e to the what? Negative 4t. So that's your solution. Back in the real world, your y is equal to e to the negative 4. Well, we have those initial conditions, and so the initial conditions might have produced a C1 is equal to 0 or something like that. C2 equal to 0. So the initial conditions probably made some of those disappear. Okay, that was kind of fun, wasn't it? I don't know. I hope I got it right. Y of 0 is equal to 1 and y prime of 0 is equal to 0. Uh, Put them in here. Well, you would have had y, an e to the negative t power, right? And then when you put that as a solution, you should have. So we did something wrong here. Michael? What? Oh, guess we're not done. Oh, so yeah, we will need partial fractions after all. All right, let's see. Thanks, Delilah, for finding that solution. All right, so we're back to our transition here. This is going to be a over s plus 1 plus b over s plus 4. So let's so there's a method that they taught you guys in Calc 2 or whatever. But there might be another method that might be useful. Um, and that's let's first get the common denominators out of the way. So we have s plus 5 is equal to a, s plus 4, b, s plus 1. And then, you'd set up a system of linear equations this way. But instead of doing it this way, there's this thing that they call the cover-up method. Um, and looking at this equation, there's no more fractions, right? So if we're looking at that equation, I can like casually just let s equal to something. So let s equal to -1, which you wouldn't have been able to do in the previous equation because there's denominators that would go to 0. But in here, if you let s equal to -1, I have -1 plus 5 is equal to a times -1 plus 4 plus b times -1 plus 1. So that goes away, and then now you have a value for a. Yeah. Yeah, sometimes if you have multiplicities, then this won't work so well. It could still work for you to be able to find one or two letters, but not all of them. All right, so what is A equal to here? 4/3? Is that what you got? And then we'll do the same cover up, but this time we'll cover up the other one. Let S equal -4. And then we have 1 is equal to 0 and B times -3. So now our y of S is equal to A, that's 4/3, plus B minus 1/3. And then now transform that back. You're going to get 4/3, and this is an e to the -t minus 1/3 e to the -4t. So this is going to be your solution. Is that right? So back to the real world, our solution is 4/3 e to the -t minus 1/3 e to the -4t. Okay. So this is an example where you actually have to use, yeah, that thing. Okay. So practicing this is going to be an important part of you learning this material. So you should practice. Okay. Should we do another? You guys are good with examples. We can move on, right? So let's go on to the next section. And the more we do these, the more examples we'll get to. What? Yeah. Okay, this is operations. I don't know. Operational properties. So for us, things always start at 0 and make it easy. That's how we look at functions. But we want to account for the idea that some of these things may be shifted in time in the real world or in the S world, the S variable. So here we're going to take a look at a translation in the S world. Later on, we'll take a look at a translation in the T world. So this translation tells us that if we're going to do a translation in the S world, if for some reason I'm not getting the answer that I want, but it looks like it would be an answer after a shift, then I can use this particular theorem to say that if I want to go back to the real world, I can just multiply it by e to the at by the shift. So when will that ever happen? I don't know. Let's take a look at an example where it might happen. Let's do maybe number 16 or something. You like it? Do you like my cursive L? It's not as fancy as this. Actually, my notes, the program that I used is the L is not as fancy. It has just that little tail in the front. Anyways, so let's do this as an example or of why anybody would be interested in the shift theorem. And people might be interested in this because if you look at something like this, your denominator is s squared plus 6s plus 34, and I don't think you can factor that into linear terms. It's not necessarily um, um, irreducible either. So if you were to try to like find the roots, your roots might have some complicated stuff. So what we might be interested in doing is, I don't know, what should we do? Complete the square. Let's see if we can complete the square. Let's just focus on the denominator. S squared plus 6s plus 34. And completing the square, let's see, s squared plus 6s plus something. So we add a 9, and we have to subtract the 9. And if there was a coefficient in front, you know, this is a completing the square thing. You just have to be careful. So this is an s plus 3 quantity squared. And what's 34 minus 9? 25. So now you have an s plus 3 instead of just a regular s. Just by looking at this as a denominator, and we're trying to do an inverse Laplace here, what do you think it's going to go back to in the real world? Sine or cosine, right? It's something squared plus something squared. So that seems cool. And now we have, now we need to split this up, but wait, our S is the one with a cosine. Our S here is just a regular S. If we split this up, I'm going to erase this. So probably don't copy it. Oh, man. Sorry. Hello? You want me to? Okay. All right. Okay. All right. Bye. Probably went in there. What was I doing? I was going to erase this, right? Yeah. Yeah, that's what I was going to do. I got distracted. So this is what we have. This is an S, not a 5, right? You're writing your S's different from your 5s. So this is your S. And our variable now has shifted to S plus 3. So I think what we're going to need to do is we're going to need to rewrite this with an S plus 3. So we have a 2. I want to force an S plus 3 here, which means I also need to compensate for this plus 3 that I put. Probably. So I added 3. I need to subtract the 3. I actually added a 6, right? So I actually need to subtract by a 6. So that keeps the numerator the same. I guess I don't have to erase this. So that keeps the numerator the same. And now I would have a 2 s plus 3 s plus 3 quantity squared plus 5 squared plus or minus 1, 5 minus 6, 1 over s plus 3 squared plus 5 squared. I guess there's probably one more thing that I'd like to do here before I run it through the inverse transform. What's that? And this doesn't quite look like the inverse transform that we want. How do we make this match our inverse transform? Can you look at your list? Oh, all right. So I need a 5 here, so put a 5 in the denominator. So because if we look at our list, the one that we were messing with was a sign. So if you look at the sign, the K here and the K here has to match. I know it's small. Right, Josh? Are you wearing glasses now? You haven't been complaining. I it's because they have glasses. Always talking, Alex. I don't know. So the inverse transform should look like a 2. Oh, now there's a shift, right? So according to this, our shift, this is our function. Our shift is going to be the inverse transform of the function that's been shifted. So if I want to write that down according to the formula, sorry. So I have a 2 that's sitting out there, and I want the Laplace transform of s over s squared plus 5 squared. And then here my s got shifted by 3. Or if I want to be really formal about this, got shifted by -3. Minus a 1/5. And then now I have the inverse transform of 5 divided by s squared plus 5 squared, which we know is a sign that this thing has been shifted by a factor of -3, the same. So that means this is a 2, and the function itself is, this is a cosine function multiplied by e to the whatever the shift was, right? The shift was -3. What? Oh. Yeah, with differential equations. So let's see where we got all these pieces of information from. So the regular transformation, Laplace transformation, and the shift. So we got the regular Laplace transformation and the shift. Okay. Any questions? All right. Gotta go pick up